gone over so far?
Where does the test material end?
What we get through today. All right, so let's review powers of 2. 2 to the 3rd. 8. 2 to the 5th.
32.
2 to the 8th.
256.
256.
2 to the 11th.
2048.
You better start practicing. All right. So last time we talked about having kind of memory cells. We could cross-couple NAND gates, we can cross-couple NOR gates. If we cross-couple NAND gates or NOR gates, we can make what's called a flip-flop, okay? And so the flip-flop, we can store a single bit of information, correct? Is that volatile or non-volatile memory?
Volatile.
What's volatile memory?
Power goes away, and it's gone.
Pardon?
No, that's
Okay, if you haven't got power, you haven't got any memory. Is it volatile or non-volatile? It's volatile. Is that because you looked it up or do you know it? Once you cross-couple those gates and you turn the power off,
it's not going to
and then you
matter.
bring the set bar, the reset bar line high, you have absolutely no way of knowing whether the Q is going to be a 0 or no way. Now, a particular gate may be repeatable. You keep turning it on, turn it off. It may come back to the same spot. But you take different gates or whatever, you'll have no way of knowing what they're doing. That's volatile memory. Give me an example of non-volatile memory.
A transistor with an aluminum core in the capacitor.
Okay, so some type of a floating gate that we can stick charge on. All right? We can make a non-volatile memory out of that. So your thumb drives, flash drives, those are made out of devices like that, correct? Okay, non-volatile. Okay. Static and dynamic is also means what? Static memory will hold information for how long? As long as there's power. Dynamic? Pardon? And why is it that the dynamic memory, if you don't do something with it, will go away?
The charge only passes through.
That's right. You're putting a charge on a parasitic capacitance that causes the gate to go high or low or the memory cell. And so you periodically have to read what's in there and then rewrite that information. Why do we use something like that? Because you can make it really easily tiny and get lots and lots of memory in a very small space. Everybody okay with that? Yes? All right. So our memory, we can talk about word size. Okay, so a word is going to be X number of bits long. Right? So how big is the word on your current desktop or laptop? I'm assuming most of you have machines that are 1, 2 years old, something like that. Yes, no? Okay, so what's the word size? How many bits?
32.
32 or 60.
Most of the new ones are 64. 64 bits in one word. How many unique things can you represent with 64?
A lot.
A bunch?
A lot.
Right, 2 to the 64, that's a lot of stuff. Okay. The generation before that was 32-bit words. Okay. Our microcontroller that we're going to use, its basic word length in terms of data and stuff like that, 8 bits. So 8 bits in a word. How many unique things can you specify with 8 bits?
256.
How many?
256.
256 unique things. Is that a lot?
Not compared to the computer.
It's not. So what are we going to do about that then? How are we going to be able to use, how are we going to be able to represent more things?
More chips?
More words. Okay? So instead of a data point being just 1 word long, we can take and make it 2 words long, or 3 words long, or 4 words long. Is that all right? You understand what's going on here? So inside this chunk of memory, I'm going to make this is really a strange size, okay? I'm going to make a 4 by 3 bit memory. Nobody in their right mind would make something. Okay, but we'll use it to illustrate. So there are 4 words in this little cell of memory. Each word has how many bits to it?
3.
3. Does that kind of make sense? So how many total bits in this memory?
12.
12. Everybody okay with that? So how many, now this is going to be a read-write memory, a random access memory. So some way or another, we're going to have maybe a read bar line. We'll have to have a write bar line. Typically, we're going to have a chip select bar line, and I'll come back to that, why we need that chip select and why that's important and how we form it. So we'll go through this and then we'll come back immediately to what this chip select is all about. Some may have a read-write bar line, just 1 line. This one, I'm going to have 2 lines here. So if I want to read from it, I drop this line, what, high or low? Low. So write bar. So bar means active.
Low.
Low. All right. Okay, how many I/O lines will this have? We got to put information in, we got to get information out. How many lines? Now, I've only got a few numbers up here, folks, so you haven't got a whole lot of choices. How many input/output lines?
4.
Wrong.
8.
Wrong.
3.
How many?
3.
Why 3?
Does you ever read right? And
Oh, you got the right answer, but for the wrong reason.
You have 3 bits.
I have 3 bits. Do you understand? If I want to know what's inside here, I got to have a line that's going to tell me what is that bit. So this would be I/O line. Well, let's likewise we like to always include 0 here. So that would be I/O 0. This would be I/O 1. This would be IO2 line. 3 bits of input-output information. Yes? Now, some way or another, you have to uniquely specify which one of the words you want to look at, correct? So, what word is this one up here? Pick a number. Not 59.
0.
See. Okay. So let's call this word 0. Which one is this?
1.
Word 1. Which one is this?
2.
We're counting. 2. And this one?
3.
3. Now, how many address lines will it take to uniquely specify one of 4 things?
Two.
2 to the second is what?
4.
Okay. I counted this in decimal. Let me count it like this. Everybody okay with that? So this, we need to talk about most significant bit and least significant bit. In these 2 bits here, which one would you say is the most significant bit and which one the least significant bit? And again, because there's only 2 bits, you got a 50-50 chance of getting it wrong. Actually, since it's this class, you probably have an 80% chance. Which one is the most significant bit? One on the left, one on the right.
The right.
Okay, we're going to vote on it. How many for left? How many for right? What is this one doing here? That one's a what? 0.
0.
This one is a,
1.
but what did this one do?
It didn't change.
Right? If I told you that, somebody was going to give you $4,329,
Okay.
which number out of that are you the most concerned with?
The 4.
Well, 4 is less than 9,
But it's got a higher place value.
but it has a higher place value. You understand that this would be the most significant digit, this would be the least significant digit, correct? You understand that the most significant digit in a word is the one that changes the least frequently. Doing okay? All right, so how many address lines do I need to uniquely specify one of these 4 words? 2 of them. So I'm going to have an A0 and an A1 line coming in, correct?
Mm-hmm.
Now, what am I going to do with that? Well, there was a reason that we spent so much time on combinational logic, and it wasn't to figure out insurance problems. So how do you fix me up something that's going to let me know if I have A0, a 0, and A1, a 1? I want to know that. Don't care whether it's a 1, 1, or a 1, 0, or a 0, 1. I want to know if it's 0, 0. What can I do? Okay, we're going to take an AND gate. Now what? Okay, let me show it to you and see if you... So what happens if A0 is a 0 and A1 is a 0? What do you have here?
A 1.
And
a 1.
1 and 1 is?
True.
True. What would I need to do to recognize that I have a 1, 0 going in so that that is the word that I want?
And
So once again, I have A0 and an A1. I'm going to do what?
an OR gate?
And again. And what?
Not one of them.
This guy I'm going to invert. That one runs straight through. Do you understand now that I have, if I want the 1, 0 word out of this mess, put a 1, 0 in, this guy's going to become a 1, and now I'll go through and select that appropriate word. So inside of memory is a whole host of combinational logic stuff to make things happen. Everybody all right with that? Yeah? So it's a 4x3 memory cell. How many address lines? 2. How many I/O lines? 3. Got this concept down? Yes? What would I do if I told you I wanted to make a 4x6 memory? And I only got these guys available to me.
4.
And right here, need two 4x3s.
Use 2 4x3s. How? So these address lines are going to go to what? Each cell, correct? So you're going to have a 4x3 and another 4x3. So the address lines there's 2 lines there. Those are going to go through like that, and then we'll have the 3 data lines coming out
Each.
that we will form 6 I/O lines. Which one is the most significant bit of the data word? Well, that's kind of up to you, right? You could say that this is going to be the most significant bit, or you could say that one. I mean, it's up to you how you wire those things up. Everybody okay with this? Yes, no? Yep.
So in the one on the right, you'd essentially be activating 2 bits at the same time.
Exactly. Exactly. Well, let's see if you got the concept. If I wanted a 4x12 memory, you have to have 4 of these guys, correct? Understand what's going on? Yes, no? Okay. All right. So